So today we are going to do question number 14 of our playlist, which is trapping inverter. It is the 42nd question of LeetCode. Okay. So what does the question say? Let's say we have an array 4, 1, 8, 2, 4, 6. That means 4, 1, 8, 2, 4, 6. These are buildings. Let's assume these are buildings. So now it starts raining. Now it's raining. Okay. These are the animations. So now the water will be stored between their spaces. Like let's say water will be stored here. It can be above this because then it will float down. But due to these two walls, the water will keep contained between these two walls. Now again, these two walls, so water will be contained here, and now these two walls, so water will be contained till this point. Can be above this point because then it will flow down. Okay, so now again water. So we assume each building is one width and height are given in the array. Height are different, but the width is 1, 1, 1, 1, 1. So now the question is asking how much total area of water is here. So let's see here, 1 height and 4 height. That means this is 3. So obviously this is 3 also because this is a rectangle and width is 1. That means 3 into 1, and let's say here. So the height is 6 till this point, and 6 here also because it is equal, and the width is 1. But out of 6, 2 height equal to 2 is the height of the building. That means this much is only 4. 4 and 1, that means 4 into 1. Now again for this point, this is 4, this is 4, this is 6, that means this is 2. So this is 2 also, and this is 1. So again 2 into 1. And there cannot be water over the first building or the last building because there is nothing on the left of it. There are walls on the right, this is the wall, but nothing to keep the water here so that no left walls. And similarly here, there are no right walls. So that means water cannot be kept on the first or last building. So we got 3 plus 4 plus 2, that means 4 into 2, 8, 24. So this is the answer. We need to return this. It's a total amount of water contained by all the buildings. So let's see what is happening actually here. Let's just take an example of just 2 buildings and see how it is working. In the last question we also did something similar, but that first question was maximum water a container can contain. Let's see if these are the 2 buildings. This is 4 and this is 8. So now you can see the width is 1 obviously. Okay, so we don't consider width, we just consider the height. In this case, we have to tell the area of this rectangle because this is the water. So we cannot take this as the height because water cannot be kept till this point, it will flow down. So we have to take the minimum height as we did in the previous question. So that means the formula for water will be minimum height of the H1 and H2. Okay, so but in this case this building height is 0. But what if this building is of 1 height? That means the minimum of the 2 is 4 and we subtract the building height from this. So we got 4 minus 1 equal to 3 because building cannot contain water inside it, only above it. So we, out of this 4 length, we remove the 1. So we get 3. Okay. So now we know the formula for water we have right now is minimum of the left and right minus the current height, the current building at which we are at right now. So let's write it down. Water equal to minimum of H1 and H2 minus height of let's say I is the index where we are right now. Now let's take another example. What if there is a 4 here and a 5 here? No, actually let's keep it like this. What if there is a 5 here, then there is a 4 here, there is a 3 here, and then there is a 7 here. So now we have to tell how much water here. Let's say this is a 0 height building. So now we can say 5 and 3. So minimum is 3 minus current height 0. We got 3. Okay. This is right? No, this is not right. Because in this case, we don't take water to this point because there is a wall. We can consider these walls. If we consider these 2 walls, then water can be up to this point, which is obviously true. Rain will not do less water. Rain will try to do as much water as possible. So in this case, we will take this wall and this wall. So how do we know which 2 walls to take? There are too many buildings. One building, another building. So for any point, any current building, if we have to know how much water will be above it, we need to take the maximum point from left and maximum from right to get the highest number of water we get, highest amount of water we can get. So let's take another example. Let's say we have to tell in this 2 building how much water will be above it. So we get, let's just there are many buildings. This is 6, and we have many buildings, and this is let's say 5. And then we have here 8, and then we have here 10. So it might look that for 2 we can take 6 and 5, so we get up to 5 height water. But this is not the best answer, because if it starts raining, the water will be up to this point, up to 8 height. So for this point we get up to 8 height, and 8 is total height, and 2 is the height of building. So we get 8 minus 2 equal to 6. At this point there will be 6 units of water here. So okay, so we now know that the formula for the water is not just H1 H2, it is a minimum of left max and right max. So let's just write it again in smaller text, so we get more space. Water at any point, at any index, water equal to minimum of L max and R max minus current height. Again we will write height of, let's say I, let's say x is the index. Okay, so now we know how to calculate the water at any one point. Now, but the question is asking the amount of water in full array. In all the buildings, we have to tell how much water can be contained. So now let's take an example and see how we can do this. First of all, the brute force, obviously. Let's say this is the array. 4, 2, 1, and then 5. So for each point, let's say this is the array is 3, small array. Okay. So now to tell the water at each point, what we need to do is we need to try all the possible left max and right max. Let's say if we have, I will just show you one index and then you can do the rest by yourself. Let's make it a bigger array, 4 and then 7 and here 8. Let's say we are at 1. For 1 we need L max, R max, and we have 1 already. We know minus 1 we have to do, but out of these two we have to get the minimum one. So we need both, and then we will tell which is the minimum. So for this we do one loop till here to get the maximum, which is 8, and one loop till here to get the maximum, which is 7. So we now get 8 and 7. We take minimum of this, which is 7, minus 1 equal to 6. So for each point we do almost a full loop, because one loop goes here, one loop goes here. So at each point, let's say we are here, so we do one loop and second loop. So in the end we can say that it is O of n for each point, and there are n points. So we get O of n square time complexity, and space is O of 1 because we don't use any external space. So this is a brute force approach. Now we did not use any space, which is good, but we did take a lot of time. Now how to optimize that? We need to take less time, because O n square is not a good time complexity. So now let's see, at each point we need the L max and R max. So instead of calculating that again and again for each point, what if we calculate all of them beforehand? So let's take an example, which is 0, 1, 0, 2, 0, 1, 0, 2, and then 1, 0, 1, 3, 2, 1, 0, 1, 3, 2, and then 1, 2, 1, 1, 2, 1. So what we're going to do, we will try to make a prefix array and a suffix array, and we will try to solve each value we want in one go, in basically one loop, which will take extra space, but it will save a lot of time. So let's say this is the prefix array. Let me make the array also, the building, so you get a better idea. This is 0, this is 1, 0, 2, and then 1, and then 0, 1, and then 3, then 2, then 1, then 2, then 1. Okay, this is the array. In these two buildings there will be no water, and only in between the other buildings, above the buildings, there will be some water. So let's say this is prefix array, this is suffix array. Prefix means left max. So at this point, what is the left max? Nothing. So we keep this as a left max. Okay. At this point, what is the left max? 1 is written 0, so we do 1. At this point, still 1, because 1 is the max. For this point, nothing on left which is max, but 2 is so we take 2. At this point, still 2. At this point, still 2. Still 2. At this point, 3 is bigger, so we take 3. Now, still 3. 3 is the biggest. 3, 3, and 3. Okay. So we got this prefix array. For suffix, we start from here. Let's make it here. Suffix start from here. We get, for this suffix we have 1 as a right max. For this 2, because 2 is bigger. For 1 we still 2. For 2 again 2. For 3 is bigger than everyone, so if we take 3. For 1 still 3, 3, 3, 3, 3, 3, and 3. Suffix and prefix we have. Now for each index we know the right max, we know the left max, we know the current height. So we take the formula minimum of the two. For 3 and 0, minimum is 0, and current height is 0, we get 0. For this point we get 3, 1, minimum is 1, current height is 1, so we get 0. For 0, we know left 3 and 1, minimum is 1, minus 0 equal to 1. That means 1 point of water. We can do the same for each point. So now we got O of n time, because we do it one loop to prefix, one loop to get suffix, and one loop to tell the total water. We summed all the water points, water values. So we did O of n, actually 3 loops, but we can consider it as O of n only. And space was also O of n, actually 2 arrays, but we can consider O of n. So this is better than last one because we were able to decrease the time, but we did use extra space. This is the best time we can get, but what about space? What if we can decrease it a bit? Let's try another approach. You can see that at any point, let's say we are at here, we just want this value and this value, but we have all the values. Why do we have all the values? Why are we storing all the values when at each point we just need two values? And the values are also monotonic. Left max goes from here. At each point, left max decide based on the left max of this value. If we know what is the left max at this point, and now we are at here, so we know this is 1 and left max is something, so now we can tell the left max of this point. So for left max of any element, we just need the last element's left max. We don't need every element. Let's say there are a lot of a very large array. Let's say there are 10 to the power 5 elements. So for this element, we just need the left max of this point. We don't need the left max of each point of the full array. So this is the kind of hint to do it in O of 1 space. If we don't store array. Let's take this example again and try to solve it using an approach, the two pointer approach, in which one pointer will be at the starting and one pointer will be at the end. Let's take this example again. 0 1 0 2 1 0 0 1 0 2 1 0 0 1 0 2 1 0 1 3 2 1 2 1 1 3 2 1 2 1. Let's make the buildings. It is 0, it is 1 0 and then 2 and then 1 0 1 and then 3, then we have 2, then we have 1, then we have again 2, then we have 1. Okay, so we will just keep two variables. Let's say one is our L max and another is our R max. These are the values we store at each point, R max, and then we have two pointer, one is I and one is J. Okay, so as I is 0, this is the left part, this is the right part. As I is 0, that means the left max we have seen so far. The maximum value we have seen on the left of this point is 0. We upgrade as we take this value and compare it to the max. It was 0 before, it was still 0. For right, we do the same. R max equal to, it was 0 before, now it's 1. Now we see for this point, we have the current value, which is 0. We have the left max value, which is 0. But we don't have right max value yet because there are many elements on right, but we only have one right max. But as we can see at this point, the left max, let's assume this is the R max is right for this point. We ignore all the values. Let's say this is the right max, this is the left max, and these are the current value. So now we can say that L max, let me make the black pen. L max is less than R max. Okay, L max less than R max. So if we have to take the border, I am saying that L max is the minimum one. So we can just do L max minus current height 0, 0 minus 0 is equal to 0. Now you might say, how do we know it is minimum? What if this one is minimum? Now let's say, because like right now we know 0 less than 1, that's for sure. So we can say this. But how do we know that R max is right? What if there is a better answer in this side? Okay. So what if there is a greater number or what if there is a smaller number? The answer might change. Now let me explain to you how it works. J is here. Let's say L max is still 0. Okay, but in this point, okay, you know what? Let me just do the loop a few times and then I will explain eventually. So now let's just assume that my approach is right and this is L max, this is R max, and then what we do is we take the water. So we get the L max is minimum. So we got 0 minus 0 equal to 0. So there is 0 water here. Now as we have done with this point, we move the left pointer. So we now I is here. Okay, let me erase this. And okay, now R stays there only, R max says that. Now I is here, we have 1, so L max is 1. Now at this point, both are equal. So anyone can minimum. Let's take another, again, L max is the 1. Now again, we have a minimum L max minus the current height 1 equal to 0. So here 0 water also. Now we move I again. Now we have 0, max is 1, so we don't update it. Okay, now at this point, we can see that, okay, these are both are still equal. So again, we do, let me erase this. Again, we do the minimum, we can take element, so let's say left again. Okay, you know what, as both are equal, let's consider this as the minimum. Okay, so now we do minimum minus the current element. Current element is, let's process the right one. So we have 1, R max minus 1, that means 1 minus 1 equal to 0. So we get 0 water here. Now we move J. Now J is at 2, so we update 2. And now at this point, see, L max is 1 and R max is 2. That means L max is the smaller one. So in this formula is used, the L max is smaller one, we want a smaller, so we want 1. That means 2 and I is here. Okay. Okay. So at this point, we know one value is 1 That's for sure, because there is nothing greater than right. And we assume that this wall is the right max. But what if there are other walls? Now I will tell you the case that I was telling before. Let me erase this a bit. J. Okay, so there are two cases. One case can be, what if there is a greater wall here, and second case is, what if there is a smaller wall, and we are consider R max here. Okay, so first of all, take the smaller wall case. This is 2 and this is 1, and we are here right now. We know this is L max because there is nothing greater than this on the left. That's for sure. This is right, but we are not sure about this. So what if we get a smaller value? Let's say we get 1. What if, let's say it was 12, let's assume for a second, and it was 12. So what if there was a smaller value on the left, which we haven't processed yet, and we just concluded this is R max? What if it was 6? In that case, for this is not R max, this is R max, because we need the R max. That means the maximum value. As I said before, if there are two walls, 6 and 5, and there is 10 here, so we take the 10 one. We don't take 5 because we need maximum water. The rain will not do like indifferentiality. It will keep the same. Okay, so that means if we take a smaller value, that doesn't matter. We need the higher value as possible. Now it comes a different case. We assume these are the walls. But what if there's a better value here? Let's say we have 10. Then that should be R max, right? Why are we taking this in R max? So in that case, if we move, let's say we take this as R max, but the formula says the minimum of the both. So 1 and 10, the minimum is still 1, the limiting factor, as I did in the previous video for the container with more water. It can be 10, it can be 100, it can be 1000. Doesn't matter, because we still take this L max minus current water, because this is the minimum one. Out of two walls, the minimum wall is taken as the limiting factor, and then we subtract the height from that. So we don't need to traverse more. We can assume that this is R max and solve it based on that, because we just need a candidate R max. We don't need the actual R max because L max is sort of smaller. That's why the formula says if L max less than R max, then we process this point. If this was the other case, if the other case, let's say if R max was 1 and L max was 5, then we assume, assume that this is L max, this is right, even though we don't know. For this point, let's assume let's say this is 5 here. Let's assume for a second. So for this point, let's assume this is the right L max, and we know for sure R max is right. And that is only the truth we need. We don't need to know if this is right or not. Even if we get a smaller value, then that means this is still right. If we get a larger value, that can be the L max, but the answer doesn't depend on that. Answer only depends on this one. So we just take one value, the shorter one. Okay, so where were we? We were at I is here. Again, L max is 1, R max is 2. So we take a smaller one. 1 minus current height is 0. That means 1. So the water here is 1 point. Let me add it blue color so that it is more visible. The water here is 1. Okay. Now again, we have done this point. So we move I. We move I again. I is here now. Now I is at, it was 2. So I updates 2. Again, both are equal. We can process anyone, either this one or this one. Let's say we do this one because we are doing I a lot, and now we are not doing J. So okay, so at this point, J was here, max was updated, but we processed this one. Okay, so now J is here, L max is 2, R max is 2. We know R max is 2 for sure. L max we assume because it is equal, so it doesn't matter. We take the minimum. Minimum is 2. Let's say. So we take 2. R max minus current height is 2, so we get 0 water. So 0 water here, we move J again. Now J is at 1, both are still equal, so okay, we can move anyone. Let's move J. So we have minimum height, let's say 2, and current height is 1, so we get 1. That means one amount of water will stay here, 1. Okay. Now we move J again because we have just processed J. Now we got 2, we still have 2, doesn't matter. Both are equal, process anyone. Okay, so now comes the interesting part. Now we move. Now we do again 2 minus 2 equals 0 because no water here, because minimum is 2 and the current height is 2. Now we move J again. Now at this point, J is now at 3. Okay, now comes the interesting part. Now we update this 3. Now we check L max is 2 and R max is 3. That means smaller one is this. So we cannot process this one. We will process this one. Let's say, what if we process this one? What if we broke a rule? What if we say it doesn't matter, we will take R3 only? No, actually, that not 3. At this point, what if we break the rule of processing the smaller one first? What if we process this? The formula is minimum of the 2 is 2 and current height is 3. So we get minus 1, which is not possible. Water can only be either 0 or like greater than 0. How can water be minus 1? That means water is taken above ground. This is not possible. So that's why the rule says the smaller one should process first. So in this case, I here, J here, left max is smaller. That means left part needs to be processed. Okay. So we have smaller one, 3, 2, smaller is 2, current height is 2. We get 0. That means no water here. We move I again. Now I is 1, value is 1, so we don't update it because 2 is greater. For this point, we need a minimum of 2, 2 and 3, minimum is 2, and current height is 1, so we get 1. That means one amount of water will stay here, and we move I, and one amount of water stays here. Now we have 0, minimum is 2, 3, minimum is 2, and water is 0, so we get 2. That means move I, and 2 more points of water stays here. Now again 1, left max is 2, right max is 3, minimum is 2, and water is 1, that means 2. So that means 1. So that means one amount of water stays here. Now again, let's say move I again, we get 3, we update 3. But now at this point, okay, you know what, let's process this one as well. I can also calculate water here. It will only break after this, once I and j overlap. So at this case, left max is 3, right max is 3, take any one, both are minimum, let's say 3. Current height is 3, so we get 0. You see, previously we get -1 because we broke the rule. But if we keep with the rules, we get 0. That means no water here. Now we move I again. Now j is here at 3 and I is at 2. That means I and j had overlapped. That means now we cannot solve it because we have already solved all the walls. So now we got the answer. 0, 1 here, plus 1, plus 2, plus 1, plus 1. That means 1, 2, 3, 4, 6. Answer is total amount of water was 6. We are able to do this in O of n. One loop, either I goes till here or j goes till here or ij meets somewhere in between, that we did in this example, and space is O of 1. So this is the most optimal way to solve this question. It was similar to the previous question we did, it was contained with most order. So with that, we have completed the 2-point section, and now we will start with sliding window. Okay, so thanks for watching, and I will see you in the next video.